In our previous video, we talked on more exponential form of complex number and the logarithm of complex number. And the video before the last, we talked on the division and the multiplication of complex numbers in polar form. Now let's take a quick recap because we'll be talking on DeMoivre's theorem there. And let's recall saying that z given z1 is equals to r1 argument theta 1 and z2 is equals to r2 argument theta 2. Then the product of this complex number will be the product of the modulus and the addition of the argument. And thereafter, we also said that the division z1 divided by z2 is r1 over r2 modulus or argument of theta 1 plus theta 2. Let's take for instance that z1 is equals to z2. Okay, so let's say z1 is equal to z2, that is they are alike. So we can say z is equals to, let's say, r argument theta. So what happens when we say z multiplied by z, right? So this will give us r argument theta multiplied by r argument theta. So this will give us r multiplied by r and theta plus theta, which will give us r squared and 2 theta. And remember that this gives us z squared. Also, z raised to power 3 is z multiplied by z multiplied by z, which is r argument theta multiplied by r argument theta multiplied by r argument theta. And this will give us r multiplied by r multiplied by r argument theta plus theta plus theta. So this will give us r raised to power 3 argument 3 theta. So considering this, we can now come to a conclusion that given z is equals to r argument theta, which can also be written as r into cos theta plus I sine theta, we can say z raised to power n is equals to r raised to power n argument n theta, which is equals to r raised to power n into cos n theta plus I sine n theta. Good. So let's take a quick example on this. We're given 4 of cos 50 degrees plus I sine 50 degrees, and each should be squared. Now, according to the law, to this principle that we have here, we can say that our r is equals to 4 and our theta is equals to 50 degrees. Therefore, it will give us r raised to power n, and the n is equals to 2, as we have here. So we can change the r to 4, change the n to be 2, multiply by cos the n is 2, the theta is 50 degrees, plus I sine 2 and theta 50 degrees. So in essence, we have 16 into cos 100 degrees plus I sine 100 degrees. Let's take another example. We're given 3 cos 110 degrees plus I sine 110 degrees to be z, and we are required to evaluate z raised to power 3. Now, we are going to compare z to be equal to r cos theta plus I sine theta. Therefore, we are saying our r is equals to 3 as we have here, and our theta is equals to 110 degrees. And we are expected to find z raised to power 3. So our n as the power is equal to 3. So we recall that if z is equal to r cos theta plus I sine theta, then z raised to power n is equal to r raised to power n cos n theta plus I sine n theta. Therefore, z raised to power 3, as the question implies, is r raised to power n, and our r is 3. Our n is also 3 into cos our n, which is 3, theta is 110 degrees, plus I sine 3 theta 110 degrees. Now 3 raised to power 3 is 27. 3 multiplied by 110 is 330 degrees, plus I sine 330 degrees. So having come to a conclusion that given z, let's rewrite, given z is equals to r into cos theta plus I sine theta, which is equivalent to r argument theta, then z raised to power n is equals to r raised to power n into cos n theta plus I sine n theta, which is also equivalent to r raised to power n argument n theta. Now we have been able to evaluate z squared, z cubed. We can also take it up to z raised to power 4 as the case may be. What happens when we want to evaluate z raised to power half, z raised to power 1 over 3, or even z raised to power 1 over 4? And it can continue on z raised to power 1 over 5. Now we know that z raised to power 1 over 2 is the square root of z. Z raised to power 1 over 3 is the cube root of z. Z raised to power 1 over 4 is the fourth root of z according to the law of indices, and z raised to power 1 over 5 is the fifth root of z. Having understanding this, we can now proceed into applying DeMoivre's theorem to find the roots of complex numbers. Roots of complex numbers. Now, let's take for instance, we are given z to be equals to 8 argument 120 degrees, and we are asked to evaluate the two square roots. Okay, to evaluate the two square roots of z. Now that means we want to evaluate z raised to power half. Now applying this to this, z raised to power half we can say that it is r raised to power half into 1 over 2 theta, because if z is equal to r argument theta, z raised to power n is r raised to power n multiplied by n theta. Now since n is now 1 over 2, 1 over 2 and 1 over 2, we can see that it is equivalent. So therefore, our arg in this case is 8 and our theta is 120 degrees. So z raised power 1 over 2 will give us 8 raised power 1 over 2 argument 1 over 2 times 120 degrees. Now in essence, the square root of 8 is 2 root 2. That will give us 2.828 argument 60 degrees. Now this 2.828 is regarded as the first square root, or is regarded as the first of the square roots. Now since we are required to find the two square roots of z, this is the first square root. Now how do we evaluate the second root? How do we evaluate the second root? In this case, we want to apply an extended form of DeMoivre's theorem, such that the other root, this is the key, it says that the other root will be distributed round the diagram, this Adam diagram, at regular intervals of 360 degrees over n. So therefore, if we are to evaluate square roots, that is two square roots, the complex number of the square roots will be separated by 360 degrees over n, that is over 2, because n is equals to 2, which is 180 degrees. And if we are evaluating the three cube roots of the complex number, the three roots will be separated by 360 degrees over 3, and that is 120 degrees. If we are evaluating the fourth roots of a complex number, each resulting complex number will be separated by 360 degrees divided by 4, which is 90 degrees. And it continues in that order. You have to find the 5/5 roots. They will be separated by 360 degrees over 5, and which is 72 degrees. Now, in this case, the modulus of the square root of the root, whether the square root, cube root, fourth root, fifth root, or the sixth root, are the same. It is only the argument that is changing. Now let's go back to our question. We can see that 2.828 argument 60 degrees is the first square root. Now we want to evaluate the second square root. Since it is 2 square roots, the argument will be separated by 180 degrees. So we have z to be equal to 8, the question 8 argument 120 degrees, and we wanted to evaluate the two square roots. After applying DeMoivre's theorem, we found out that the first square root is equal to 2.828 argument 60 degrees. Now the second square root will be equal to 2.828 argument. Remember, this is separated by 60 over n, and that's 180 degrees. So it's separated by 180 degrees, which will be 60 degrees plus 180 degrees. So this will give us 2.828 argument 240 degrees. So in essence, we are saying the first square root is equal to 2.828 argument 60 degrees, and the second square root is equal to 2.828 argument 240 degrees. Now if we draw these on an arc diagram, we can see this is the first square root z1 at an angle of 60 degrees, and this will be the second square root z2 at an angle of 240 degrees. Now to understand further, we want to apply the same question, but this time we want to find the three cube roots of a complex number. So given 8 argument 120 degrees, evaluate the three cube roots. The first thing to do is to evaluate the first root, and the first root can be done using DeMoivre's theorem, such that we recall that if z is equal to r argument theta, then z raised to power n is equal to r raised to power n argument n theta. So we are asked to evaluate z. If z is 120 degrees, we want to evaluate z raised to power 1 over 3, because we are dealing with cube roots, will be equal to, here in this case, r is equal to 8 and theta is equal to 120 degrees. So applying the formula, we have 8 raised to power 1 over 3 argument 120 degrees divided by 3. So this will give us the first cube root. This gives us the first cube root to be 8 raised to power 3. 8 raised to power 1 over 3 is 2, and 120 degrees divided by 3 is 40 degrees. So this is the first cube root. Now how do we evaluate the remaining cube roots? That means the second and the third cube roots. The first thing we go back to look at is how much degrees, by how much are those roots separated. Now 3 cube roots, they are separated by 120 degrees. Therefore, second cube root will be equal to 2. Remember, we are separated by 360 degrees over n over 3. That's 120 degrees. The second cube root will be 40 degrees plus 120 degrees, which will give us 2 arguments 160 degrees, and the third cube root is separated from the second cube root also by 120 degrees. So the third cube root is equal to 2. We will take this 160 degrees plus 120 degrees, and this is equivalent to 2 argument 280 degrees. Now the rest is to draw an argand diagram. So we can call the first cube root to be Z1, we can call the second cube root to be Z2, we can call the third cube root to be Z3. Now with respect to that, you can say the first cube root is at an angle of 40 degrees, Z1. The second cube root is at an angle of 160 degrees. We can call this Z2. And the third cube root is at an angle of 280 degrees, which we will call Z3. So this is a pictorial representation This is a pictorial representation of the three cube roots of 8 argument 120 degrees. Let's take two more examples. Now we are given Z is equal to 5 cos 225 degrees plus I sine 225 degrees. And we are asked to evaluate the three cube roots and display the roots on an argand or the argand diagram. Now we evaluate the first cube root using DeMoivre's theorem. Okay, so the first thing we can do is to convert this Z in terms of 5 argument 225 degrees. So we can say the R is equals to 5 and the theta is equals to 225 degrees. Now we can evaluate the first cube root, that's Z1, using Z raised to power 1 over 3 because we are dealing with cube, which is equal to 5 raised to power 1 over 3 into 225 degrees divided by 3. So in essence, the cube root of 5 is 1.7099, which we can approximate to be 1.71, and 225 degrees divided by 3 is 75 degrees. Now this is called the first cube root. What then is the second cube root, and what also is the third cube root? Second cube root is Z2, the third cube root is Z3. Now recall that they are separated by 360 degrees divided by n. Now in this case, n is equal to 3 because we are dealing with cube roots. So definitely the separation amongst between the roots is 360 degrees divided by n divided by 3, and that's 120 degrees. So if the second cube root is separated from the first cube root, by 120 degrees, then Z2 is equals to 1.71 argument 75 degrees plus 120 degrees. And this will give us 1.71 argument 195 degrees. And if this third cube root is separated from the second cube root by 120 degrees, then the third cube root Z3 will give 1.71 argument 195 degrees. We are taking this plus 120 degrees. Now this will give us 1.71 argument 315 degrees. Now we have the three cube roots. Z1 is equals to 1.71 75 degrees. Z2 is 1.71 argument 195 degrees, and Z3 is 1.71 argument 315 degrees. Now we can now draw an Argand diagram represents the three roots. So this will be a representation of the first root at 75 degrees, and this will also be a representation of the second root. Just a sketch at 195 degrees, and finally this will be the representation of the third root at 315 degrees. Now, as we conclude, let's pick a question that deals with fifth roots, where we are required to find 5 roots. Now, let's go to question 4. We are given the complex number of z is equal to 12 argument 300 degrees, and we are required to find the 5 fifth roots. To find the 5 fifth roots, the first thing is to find the first root, that's z1, and using that z1 we evaluate it using DeMoivre's theorem. So z1 is equal to 1 over 5, which will give us 12 raised to power 1 over 5, argument 300 degrees divided by 5. So in essence, 12 raised to power 1 over 5 is, using your calculator, the fifth root of 12 is 1.644, and 300 divided by 5 is 60 degrees. Now we are dealing with 5 roots here, so by how much are they separated? And our answer will be 360 degrees over n, and n in this case is 5, and 360 divided by 5 is 72 degrees. So in essence, our second root is 1.644 argument 60 degrees plus 1 plus 72 degrees, and that will give us 1.644 argument 60 plus 72, 1.644 argument 132 degrees. Z3 is separated from Z2 by 72 degrees, so this will give us 1.644 argument 132 degrees plus 72 degrees. Remember, we are taking the one preceding it, which will give us 1.644 argument 204 degrees, and Z4 is 1.644, argument 204 degrees separated by 72 degrees. This is 1.644, argument 276 degrees. And finally, Z5 is equals to 1.644, argument 276 degrees plus 72 degrees. This gives us 1.644, argument 348 degrees. Now, this can be sketched on an Argand diagram. Okay, let's minimize the space here. So we can sketch it on an Argand diagram there. And we know that this will be Z1 at an angle of 60 degrees. And Z2 is 132 degrees. 132 degrees lies here. So this is Z2. And 204 degrees, which lies in the third quadrant, is about here. Z3. 132 degrees is in the second quadrant. 204 degrees is in the fourth quadrant, is in the third quadrant. And 276 degrees is in the fourth quadrant, very close to the fourth quadrant. So this is Z4 at an angle of 276 degrees, and Z5 is 348 degrees. Z5. Now, to make it more neater, we can just draw without showing the angles. So this will give us Z1 at an angle of 60 degrees, Z2, Z3 at an angle of 204 degrees, which is the third quadrant, Z4, and finally Z5. Remember, the vertical axis represents the imaginary axis and the horizontal axis represents the real axis. So with this, we can be able to evaluate roots of complex number. So in this video, we talked on DeMoivre's theorem and roots of complex numbers. In our next videos, we will pick questions on more questions on evaluating roots of complex number.